Welcome! Today we are diving into a modern state architecture centered around the repository pattern. Our goal is to decouple data management, caching, and UI logic using TanStack query and signals. The architecture is divided into three logical tiers. At the top, the UI layer focuses exclusively on component rendering and user interaction, whether you're using React or Angular. In the center, the repository layer acts as the engine for data management and caching. By utilizing TanStack query and local storage here, we can handle complex state hydration away from our view logic. The base is the adapter layer, which provides a network abstraction for fetching data from REST APIs, GraphQL, or WebSockets. Notice the signals and data flow on the right. User interactions in the UI layer send mutation signals down to the repository. As the repository and adapter layers process data, they send signals back up, triggering reactive updates and ensuring seamless state synchronization across the application. This approach is highly versatile and applicable to both React and Angular ecosystems.
State management often becomes chaotic as applications scale. On the left, we see the reality many developers face, a tangled web of scattered UF effect hooks and deep prop drilling that makes code difficult to maintain and reason about. To solve this, we are shifting toward the structured architecture shown on the right, utilizing a repository and adapter pattern. Our goal is to combine the strengths of TanStack query for managing asynchronous server state with signals for synchronous reactive state. In this model, the adapter handles data normalization and external communication, while the repository manages the business logic and data access. Signals then provide a high-performance way to bridge this data to the UI. The key outcome of this transition is total decoupling. By moving logic out of the component layer, we protect the UI from the inherent complexity of data fetching, caching, and state synchronization, leading to a much cleaner and more scalable codebase. The three-layer schematic provides a structured framework for decoupling application logic and data flow. At the foundation, layer 1 is the adapter, which manages infrastructure. This is a dumb translation layer that handles the technicalities of HTTP verbs and endpoints while remaining entirely stateless. Above it sits layer 2, the repository, which serves as the domain. This layer acts as the brain and the single source of truth for the application, orchestrating data fetching via TanStack, managing caching, and maintaining reactivity through signals. Finally, layer 3 is the UI or presentation layer, referred to as the reader. Its role is intentionally limited. It simply displays the signals exposed by the repository to the end user. This architectural approach ensures a clear separation of concerns, making the system easier to maintain and scale. Layer 1 is the adapter, also known as the infrastructure layer. This layer acts as the primary interface between our application and external systems, such as a backend API. As illustrated by the code snippet, the user adapter serves a single purpose, handling raw network communication. It uses an API client to perform standard operations like fetching all users or updating a specific record. Key to this architecture is that the adapter layer consists of pure TypeScript or JavaScript. It contains absolutely no UI logic, framework-specific code, or complex business rules. Instead, it focuses entirely on mapping domain actions to specific HTTP verbs and endpoints. By isolating these external dependencies here, we ensure that the rest of our application remains decoupled from the implementation details of our data sources. Moving into layer 2, we have the repository, which serves as the core of our data management system. Within our class service, we utilize two key technologies working in tandem. First, TanStack query is responsible for the heavy lifting of data orchestration, handling critical tasks like caching, deduplication, and automatic retries. Alongside it, we use signals to provide fine-grained reactivity. As data flows in from our adapters, it is processed through these systems to output reactive signals. This architecture establishes the repository as the single source of truth. By having the UI subscribe directly to a signal, we create a powerful abstraction where the interface remains completely agnostic of the data's origin. Whether the information is retrieved from a local cache or a fresh network call, the UI simply reacts to the signal updates seamlessly. Moving into layer 3, we focus on the UI, or presentation layer. At this stage, the component's responsibility is strictly limited to rendering the current state.
As demonstrated in the code snippet, the component simply maps over the user's list directly from the user repository. By leveraging signals, the UI remains reactive without the need for internal state management or complex lifecycle hooks. This architectural approach allows us to completely eliminate use effect within the presentation layer, resulting in cleaner, more declarative code that is significantly easier to maintain and test. Now, let's examine the technology stack implementation for both React and Angular. On the React side, we utilize Axios for network requests and incorporate the Preact signals package for reactivity. For caching and server state management, we rely on TanStack Query version 5, with the option to use Jotai for more complex local state needs. Switching to the Angular stack, specifically version 17 and above, we leverage the built-in HTTP client for networking and native Angular signals for reactivity. To provide a consistent caching experience, we are implementing the experimental TanStack Query for Angular. This side-by-side approach ensures that both frameworks are using the most modern, signal-based architectures available. In this deep dive, we explore the implementation of a class-based repository to manage query logic independently of the React component lifecycle. By adopting this service-oriented approach, we can synchronize TanStack query data with signals while effectively keeping hooks out of our core business logic. Looking at the user repository implementation, we first define our signal state using the signal primitive. This provides a reactive data source that can be consumed throughout the application. The architectural bridge here is the query observer. Unlike the standard use query hook, the query observer can be instantiated and run entirely outside of React components, allowing the repository to manage data fetching and caching independently. The final step in this pattern is the synchronization process. By subscribing to the observer, we listen for any updates within the React query cache. When new data is received, it is immediately pushed into our signal by updating its value. This pattern ensures that our state remains reactive and up-to-date, while maintaining a clean separation between data management and the UI layer. In this deep dive into native integration, we examine how Angular's inject query fundamentally simplifies state management. By automatically providing results as signals, it reduces the necessary bridging code to an absolute minimum. Looking at the user.repository.ts example, the inject query function serves as our single source of truth. It manages the lifecycle of the data fetch using a specific query key and function. To expose this state to our components in a reactive way, we utilize Angular's computed function. Here, we derive the user's list and the isLoading state directly from the query. This ensures that any changes in the query status or data are reflected instantly throughout the application. Furthermore, handling updates is streamlined with inject mutation. In this scenario, when a new user is created, the onSuccess callback triggers a refetch of the primary query, ensuring our UI remains synchronized with the server-side state. This seamless integration between TanStack query and Angular signals creates a robust and highly readable repository pattern. In this slide, we examine the physics of performance by comparing the virtual DOM with signals. In traditional React architectures, the virtual DOM acts as a middleman. When state changes, the framework must perform a diffing process across the component tree to identify exactly what needs to be updated. This results in a diffing cost of O of n, meaning performance is tied to the overall size and complexity of the tree. On the right, we see how signals provide a more efficient alternative. By utilizing a technique known as vnode skipping, signals allow the framework to bypass the traditional diffing bottleneck entirely. Instead of traversing the tree, a signal establishes a direct link to the specific element that needs to change. This reduces the update cost to a constant O of 1, ensuring high performance and surgical precision in UI updates, regardless of application scale. Vnode skipping is a process where the component function does not rerun when state changes. When a signal value change occurs, the framework triggers a targeted update directly to the text content of the element in the real DOM. As illustrated here, the component lifecycle is completely bypassed, meaning the framework avoids the computational cost of re-rendering the entire component. This allows for highly precise updates that target only the necessary parts of the user interface without the overhead of traditional virtual DOM reconciliation. Signal slicing is an advanced pattern designed to address a common performance bottleneck. Updating a large object signal often triggers far too many listeners. When a single property in a large state object changes,
every component or effect observing that object is notified, which can lead to significant overhead and unnecessary UI re-renders. The solution is to leverage derived signals through the computed function. This allows us to slice out only the specific pieces of data a component actually needs, isolating it from unrelated changes in the parent object. Looking at the first code example, we define user count as a computed value. Because it specifically tracks this.users.value.length, the UI will only update when the number of users changes. If a user's profile information is updated but the total count remains the same, the UI elements tied to user count will not be triggered. In the second example, we create a slice for the active user. By using computed to find a specific user within the array, we ensure that the UI focusing on the active selection isn't forced to re-render every time there is a change elsewhere in the list. This strategy provides fine-grained reactivity, ensuring that our application remains performant by only processing the specific data slices that are relevant to the task at hand.
Optimistic updates are a key strategy for enhancing user experience by making interactions feel instantaneous. This diagram illustrates the standard flow for managing mutations. It starts with the signal update, where local state is updated immediately in response to a user action. This triggers the UI home phase, ensuring the user sees the change reflected in the interface without delay. While the user interacts with this updated UI, an asynchronous API call is initiated, where the adapter sends the request to the backend. If the request is successful, we enter the confirmation phase and invalidate the relevant query to ensure our local cache is perfectly synchronized with the server's data. However, if the request fails, the rollback mechanism is engaged. This reverts the initial signal update to restore the interface to its previous state, maintaining data integrity and keeping the user informed of the failure. This architecture impact analysis highlights the transformative benefits of moving from an unpatterned approach to one utilizing a repository pattern. Currently, our data fetching relies on scattered use effect hooks, which are difficult to maintain. By implementing a centralized adapter, we consolidate these calls into a predictable, single source of truth. Regarding state synchronization, we are transitioning from manual use state management to an automated system powered by TanStack Query, which handles caching and state updates seamlessly. This change also addresses reactivity. Instead of relying on prop drilling that triggers expensive tree re-renders, we can achieve surgical updates at the node level, significantly improving performance. A key advantage of this architecture is the separation of logic. We are moving away from UI components that contain complex business logic toward dumb UI components focused strictly on presentation, while the repository handles the core logic. Finally, this structure simplifies our testing strategy. Rather than struggling with hard-to-mock components, we can easily isolate and mock the repository to ensure our business logic is robust and reliable. The verified blueprint outlines a modern state architecture designed for maximum performance and maintainability. By decoupling business logic from the view layer and implementing the repository pattern, we create a clear separation of concerns that simplifies testing and scaling. We leverage signals to ensure high-speed, granular reactivity across the application, while integrating TanStack to provide a reliable foundation for data synchronization and state management. This architectural strategy transforms how we bridge the gap between back-end data and the user interface, resulting in an application that is both resilient and exceptionally responsive.